Hi everyone! In this video, me and my group members will be presenting a topic called access function and regular solutions. So let's get started. Before we start, I'm going to introduce my group, which consists of 6 members. First, we have Aidana Nur Nadia binti Aidil Hairi, Wan Asma Samiah binti Wan Mokhtar, Nur Aina Nazifa binti Muhammad Norazman, which is me myself, Fariza Hanim binti Abdul Aziz, Nurul Akilah binti Abdullah, and lastly, we have Zatilah Kamarina binti Muhammad Arif. The outline of the presentation will include access functions, regular solution, examples of graph, and lastly, a few questions regarding our topic. First, let's take a look at the access function. So, what is access function? Well, access functions are used in chemical thermodynamics to illustrate how a mixture's property differs from an ideal mixture. According to its definition, the access function is the discrepancy between a mixture's ideal and real properties. For instance, the distinctions between a mixture's real and ideal Gibbs free energies is what is meant by the term excess Gibbs free energy. The behavior of actual mixtures may be predicted using access functions, and the interactions between the mixture's constituent parts can be understood. In terms of mathematical explanation, some functions of interest may vary slowly, and it is then advantageous to put it as a simple function, for example a straight line plus a deviation. The most common case is the local expansion of the function as the tangent line at a given point of interest plus its deviation. The concept of access functions is similar to that of residual functions. However, the access functions are restricted to mixing. Both illustrate the distinction between a real state function and an ideal state function. The mixed parameter is calculated by subtracting the sum of the separated pure components for both the ideal and real systems. Access functions typically follow a specific restriction. Example for regular solution is solid solutions with a random structure. Here, omega describes the difference of the nearest neighbor interaction energies between the molecules UA minus A, UB minus B, and UA minus B. Beta equal to omega divided by RT is the corresponding dimensionless parameter which shows a strong temperature dependency. Link to caloric data. When at omega with beta smaller than 0, mixing is exothermic where heat will be released. For example, are chloroform and acetone. Where omega with beta is larger than 0, mixing is endothermic where heat will be uptake, and for example, our aqueous solution of hydrophobic compounds. For normal regular solution, where Gx is equal to Hex, it is R asymmetric to x equal to 0.5. An example for such a symmetric excess enthalpy is shown in graph A for mixing of tetrachloroethane and chloropentane. As an example for a non-regular solution, the asymmetric excess volume for mixing of tetrachloroethane and cyclopentane is shown in graph B.
Next, we will see about regular solution.
Regular solution models are based on ideal entropy of mixings of the constituents, whose entropy mixing is equal to that of an ideal solution with the same composition, but is non-ideal due to a non-zero enthalpy of mixing. So the formula we got is delta H mix equal to beta XA XB, where beta is the dimensionless parameter that is a measure of the A-B interactions relative to that of the AA and BB interactions. The Gibbs energy of mixing is therefore delta G equal to delta H minus T delta S equal to RT times with XA ln XA plus XB ln XB plus delta XA XB. The basic assumption of the simplest regular solution model is that when components A and B mix randomly. To construct the regular solution model, we recall an ideal solution, which is a solution where all interactions between solution components are equal. In a solution composed of two components A and B, we call the interaction between two A molecules epsilon AA, between two B molecules epsilon BB, and between an A and B molecules epsilon AB. If these three interaction energies are equal, the solution is ideal. If they are not the same, the solution's thermodynamic behavior is non-ideal.
Next, we will see the example of graph. Next, based on the equation above, beta is dimensionless parameter that is a measure of the energy AB interactions related to that of the AA and BB interactions. If beta is less than 0, mixing is exothermic and solid-solvent interactions are more favorable than solvent-solvent and solid-solid interactions, while if beta is more than 0, mixing is endothermic. Next, for a regular solution, and based on the equation, the important feature is that beta is more than 2. The graph shows two minima separated by a maximum. At beta is more than 2, the system will separate spontaneously into two phases with compositions corresponding to the two minima.
Next, let's answer some questions. For question number 1, given the dissolving of CaCl2, the delta G of CaCl2 is equal negative 748.1 kg per mole, the delta H of CaCl2 is equal negative 795.8 kg, and then the delta S for Ca2 plus is equal negative 53.1 J per kmol. The delta S of CaCl2 is equal 104.6 J per kmol. The delta S for Cl- is equal 56.1 J per kmol. For this question, we need to calculate the temperature of this reaction. The formula is delta G equal delta H minus delta S. We need to calculate the temperature, so the formula is T equal delta H minus delta G divide delta S. Insert the information given and then we will get the answer, which is minus 34.536 K of T.
For the question 2 is identifying the parameter for a regular solution. The question is identify the value of the parameter Z that will be appropriate to model a mixture of benzene and cyclohexane at 25 degrees Celsius and estimate the Gibbs energy of mixing for an equimolar mixture. The solution is, in the experiment data, the maximum occurred close to x1 equal to xp equal to 1 over 2 and its value is close to 700 watt and 1 joule per mole. It follows that Z equal to H over RT at A and XP, where H is 701 joule per mole and R is 8.3145 joule per kilo per mole, and T is 298 Kelvin, and XA is 1 over 2 sum goes to XB, and it becomes 1.13. The total Gibbs energy of mixing to achieve the stated composition, provided the solution is regular, is therefore data mix G over N equal to 1 over 2 RT ln 1 over 2 plus 1 over 2 RT ln 1 over 2 plus 701 joule per mole, and it will become negative RT ln 2 plus 701 joule per mole, and it will become negative 1.72 kilojoule per mole plus 0.701 kilojoule per mole, and lastly it becomes negative 1.02 kilojoule per mole.
For the third question, given that 2.0 mole of hydrogen gas at 2.0 atm and 25 degrees Celsius and also 4.0 mole of nitrogen gas at 3.0 atm and 25 degrees Celsius are mixed at the constant volume, calculate the change in Gibbs free energy. To solve this question, we can calculate the change in Gibbs free energy using the equation that were given below, where T is the temperature in K, which is Kelvin, and delta S mix is the change in entropy for the mixings of gases. Given that the initial pressures of hydrogen gas and nitrogen gas are different, we can calculate the mole fractions using the ideal gas law. Mole fractions of hydrogen gas and nitrogen gas were calculated by using the ideal gas law formula, where the species of hydrogen gas itself were divided by the species of hydrogen gas by adding the nitrogen gas. Same goes to the mole fraction of nitrogen gas. By using this formula, we got that mole fraction of hydrogen gas is 0.33 and 0.67 for nitrogen gas mole fraction. The change in entropy for the mixings of gases can be calculated as the equation that was shown below, where R is the ideal gas constant, which is 8.314 joule over mole Kelvin. Plugging in the values, we get that the change in entropy for the mixings of gases is 0.091 joule over mole Kelvin. Therefore, we can proceed to calculate the change in Gibbs free energy for the mixings of gases at a constant volume by using the delta G mix equal to negative T delta S mix that were mentioned in the first box. by replacing the temperature from the degree to the Kelvin and also replacing the delta S mix that we calculated before, we get that the change in Gibbs free energy is equal to negative 9.7 kilojoule. In the conclusion, the change in Gibbs free energy would be negative 0.7 kilojoule when the initial pressures were different. From this question, I really hope that all of you will understand the theory of the change in Gibbs free energy of mixing.
This is the reference that we use based on this topic. That's all from us. Thank you for listening.